PhD under him, definitely go to postdoc in some leading universities across the world. This is his status. He has got a number of over 150 number of research publications, and he has collaborated with 28 research scholars from India and abroad. So recently, Stanford University conducted a survey and identified top 200, top 2% scientists from India. I'm happy to announce that Dr. Pradeep G. Siddeshwar is one among them. So we are more honored because Bengaluru, Karnataka has got some very few young scientists, I mean. So Pradeep G. Siddeshwar is one among them. Awards, and if I speak about awards and recognitions, it goes up to 2 pages. The major awards and recognitions being, he got President of India Award in 1983, Young Scientist Award in 1992, Indian Mathematical Society Award in 1996, Japanese Society for Promotion and Social Science Fellowship, William Monk Fellowship from University of Hong Kong, Chandana Award from University of Windsor, Canada, C.V. Raman Award, Royal Society Incoming Fellowship, London in 2007, visiting researcher in Shanghai, Jiang Tong University, Shanghai, visiting researcher in University of Nottingham, visiting researcher National University of Malaysia, visiting researcher Chile, fellow National Academy of Sciences, FNAC in 2012. So like this, I can list out so many things. See, he worked, means he served Bangalore University till 2020. Recently, he retired from Bangalore University and he joined Christ University. In Bangalore University, he was academic council member, editorial board of Vijnan Bharati member steering committee for NAC documentation, chairman project proposal committee, member UGC UPE committee, chairman technical advisory committee, member editorial board of Bentham Open Transport Journal. So like this, he has served Bangalore University to many ways. He has visited more than 30 countries on visiting assignments for delivering invited talks. With this, I'll stop brief introduction. I'll hand over to Dr. Pradeep G. Siddeshwar. Thank you, sir.
Are you hearing me?
Yes, sir.
Okay.
Sir, you are audible, sir.
Pardon?
Audible, sir.
Audible?
Yeah, there is audibility, sir. No problem.
Okay. Thank you very much. Thank you, Dr. Sripad. Thank you.
Yeah, visible, sir. Clearly visible.
Okay. Thank you, Dr. Sripad. Thank you, Principal Sir, and Head of the Department of Mechanical and many others who have conducted this wonderful international FDP. And I'm sure this will help a lot of youngsters get to know certain new topics which are in the field, or get to know better the existing ones, as experience doing some problems really matters, and doing it well matters much more than that. So now today, what I'm going to speak to you is about a very new problem, which it has been in the literature for maybe a decade now at the most. There was mention of it in the literature a few years back, and we happened to see it, and the Punjab University research group with whom we are connected they initiated some sort of work, but in a limited way. And I recently had the opportunity to propose this to one of the students in Christ University, Dr. Matthew, and Dr. Pranesh. So the three of us sat down and we were able to bring out really nice features of that aspect of Rayleigh-Benard convection, wherein regulation is an important requirement. So I'll present this new concept now, this two frequency gravity modulation, what it means, how it affects at the onset, how it affects post onset, how does it affect. So these things I'm going to tell, and during the course of this, you'll also realize that it is not just mathematics that we need to do. It is a bit of engineering as well when we take up problems of fluid dynamics. So I'll mention to the extent possible some engineering aspects of this problem, and hopefully it will drive home the point to the mechanical engineers as well, that it is possible to have a collaboration between the two departments, and quite suggestively the two departments have come together to arrange this international FDP. So now to the topic of my lecture. Now for those of you who are not familiar with what is Rayleigh-Benard convection, this is a very familiar figure. And you see that there are two plates here, okay, and from the bottom plate over here, the heat is passed to the system. When I say system, it is the fluid occupying the region between the two plates. So the lower plate is hot, the upper plate is relatively cool. So what happens is there is a temperature contrast between the plates. The fluid at the bottom becomes lighter, fluid at the top is heavier. So the fluid at the bottom that moves up, and the fluid at the top that falls down. Okay, so there is some sort of circulating cell which is seen when the temperature difference between the two plates exceeds a particular value. Why is that critical temperature difference required? It is required to overcome the viscosity and the thermal conductivity. These are stabilizing factors. So you see that there are counter-rotating cells for obvious reasons. If all of them were to be clockwise or anti-clockwise, then you see that if suppose this is clockwise and this were also to be clockwise, then in this interface there would be friction, some heat energy would have been lost. In nature, fluid always takes the path of least friction. So if one of the cells goes clockwise, the other has to go anti-clockwise. So when we talk about a Rayleigh-Benard cell, we actually mean these two together. Why is it? You see that this is one Rayleigh-Benard cell, this is another Rayleigh-Benard cell, because this is the period. Now suppose I call this as capital T, then this capital T, at every T it repeats itself. So this cell is repeated every T interval. Okay, so that is the period. So we'll come to that more. Now, regulation of this convection is very, very important, and that can be done by sort of disturbing the system through some means, maybe at the boundary, or maybe the entire system is influenced by some sort of oscillations due to vibration or whatever. And as a result of what we do to the system in the form of what we call as periodic waveforms, so the frequency, amplitude, and phase naturally help in getting the desired control of the convection process. Now, if we desire what we can do is through these external mechanisms. Hello? Someone has switched on, I think. So through these mechanisms, we'll be able to control the dynamics inside the Rayleigh-Benard system. So one way of doing it would be to have what is called as gravity modulation. And you see from here that there are two things written over here. One is minus G naught into K cap. That is the usual gravity we see, which is acting vertically downwards. We are taking Z vertically upwards, and that is the reason why we wrote minus G naught into K cap. So that is the usual gravity. Now, when we apply what is called as gravity modulation, I'll very soon explain this in great detail to you. It gives rise to some body forces. In order to make it mathematically tractable and also otherwise. For example, there is a need to maintain the nature of the dynamics within the system, and that can be done only when you do everything in a time periodic manner, in a gentle manner. The amplitudes must not be very high, the frequencies should not be very high. So the basic dynamics that you see within the system must be retained, but they must be regulated. So that is only possible when you have a time periodic phenomenon there. So here, this additional gravity, this comes about in a very nice way when you vibrate the system through some means. I'll explain that to you very shortly. Okay, so this additional thing comes due to vibration of the system. I'll explain that. So this problem of Rayleigh-Benard convection was seen way back in 1882. This was reported in the Proceedings of Glasgow Philosophical Society. I'm sorry, this should be PROC. I'm sorry about that. And here, the patterns which change due to the external influence on the system is very well explained. And fortunately, these papers which are mentioned, they are available for our reference. Okay, Benard was the first one to conduct an experiment, and what he saw was some nice cells, the likes of which I showed in the figure earlier. But unfortunately, those cells, they were formed not due to buoyancy, but were due to surface tension. Lord Rayleigh, a few years later, thought that those cells were due to buoyancy. So he provided a theory wherein the cells were explained on the basis of buoyancy forces and not on surface tension forces. So, but in any case, the convection that we see within two plates due to heating from below on buoyancy reasons, it still goes by the name of Benard and Rayleigh because Benard was the first one to observe the pattern and Lord Rayleigh gave a theoretical explanation for the problem, but a slightly different one. And excellent papers are available see, for example, if you see here, it is Glasgow, that is Scotland. Here, this is Dublin, Ireland. Okay, Royal Society, this is London. So you see that entire Ireland and the UK together have a number of societies which publish outstanding papers, and those papers are luckily available for all of us. So Proceedings of Royal Society, this is an excellent paper, you must read paper. And subsequently, after several years back, the Nobel laureate Chandrasekhar from Chicago, he brought out the book Hydrodynamic and Hydromagnetic Stability, wherein he explained just about everything you want to know. This is the book we must have. Okay, I'm sorry about this. Along with Dover Publications, we must mention the place. I'm sorry, I did not look into that. So here, is a set of experiments. In this work, it is mentioned, performed by Donnelly, wherein the convection between two cylinders, this is not Rayleigh-Benard convection, this is Taylor-Coed flow, the dynamics within between two cylinders, the annulus region that was controlled by having the rotation of the cylinders being done in a time periodic manner. It's a fantastic problem explained in a very nice way. Okay, and this is not exactly again a Rayleigh-Benard problem. It is some other problem which involves a plane free surface, and what you see on the surface, that is controlled with the help of periodic motion of the system, and that is what is called as gravity modulation. I'll tell you very soon what it means. Okay, so in the Journal of Fluid Mechanics, the first paper on gravity modulation pertaining to the Rayleigh-Benard convection, that was reported by Gresho and Sani. You have a number of papers of them reported in the Journal of Fluid Mechanics and in other journals. These are also must-read papers. Now we came out with in 2019, last year, we came up with a new type of problem wherein gravity, of course, additional gravity effects are also there, like what you see in the traditional gravity modulation problems. But what we did was, rather than take the trigonometric one, we also took square and triangular modulation, meaning instead of sine and cosine, we did take Fourier series representing those other non-sinusoidal vertical oscillations. Okay, I'll explain very soon. And we considered this in Newtonian liquids as well as Newtonian nanoliquids, and it appeared in Mechanica. I somehow have a feeling that we hurried through and published in this journal. We could have also gone in for Journal of Fluid Mechanics if a bit of subharmonics were to be added in the paper. These are two very important papers on the topic which I'm going to speak about today on two frequency modulation. I saw this paper of Besson, Edwards, and Tuckerman, who talk about the how surface waves can be originated with the help of say modulating with the help of modulating in two different ways parallelly, that is. And Renu Bajaj, she pioneered this work. She made use of two frequency gravity modulation in seeing how convection in ferrofluids can be regulated. And we used this idea, no doubt. She was the pioneer in this. We used this idea and we carried it forward, and a lot of new results were obtained. So myself, Pranesh and Ansa, we put down our results in the form of a paper, and this is presently under consideration in the physics of fluids, and hopefully it will go through. That is our wish. Anyway, now you see, this is Benard's experiment, the sketch of Benard's experiment. So what they wanted to do and how it was to be designed, everything is available in the paper. You see this sketch, how the heating is done, where the cameras are to be placed. Are the cameras to be placed sidewise? So this is the distance between the parallel plates, and where the cameras are to be put. Is it horizontal direction, or is it in the vertical direction? And how is the camera to be moved? Which is the position of importance? So various things, everything has been put down in that. And now this is the experimental setup, the modern way, how it is seen. So you see here, that these are the two plates, and for engineers, for your information, the upper plate is made of plexiglass, and the lower plate is made of metal because it needs to be heated. And plexiglass, by the by, can take reasonably good temperatures. And why do we use plexiglass on the sides as well as at the top? The plexiglass is used over here because the dynamics within the system will have to be photographed. So you'll see that within the medium, the liquid is there. It is heated from below. It has to be very uniformly heated. And mind you, if you want to see the different patterns that are that can be seen in this system, they can be seen only when it is vibration free. Now, what do you mean by vibration free? Now, for example, close by the laboratory, there might be some, disturbing agencies. For example, it could be the closing of a door, or it could be the closing of a window, or it could be someone pulling the chair, or someone driving a car, or it could be some air which comes in, or it could be any such thing which disturbs the experimental setup. So once you have these setups, you are not going to see what you want to see, but you are going to see something else. So the sensitivity of this experiment to vibrations is a very, very important thing that needs to be looked into while actually performing this experiment. So I'll talk about this a little more. So you see the photograph here in the experimental setup reported by Dr. Fau, F-A-U-V-E. You can see that paper on the net. So you'll see that the camera is positioned over here, and it is captured from the sides, meaning that the type of pattern that we are trying to see here is what is called as rolls. It could be longitudinal rolls, or it could be transverse rolls. Now, if it is longitudinal rolls, one would see over here, and if they are transverse rolls, the camera would be moved to the other side. And if it is what are called as hexagonal hexagonal cells, the camera had to be positioned vertically, and the dynamics had to be captured. So these are the things that are to be seen, and the number of frames to be captured, that also matters. We can see the dynamics clearly only if this camera is a sophisticated one. These are all the practical things that are needed to be looked into in order to do a very good experiment concerning Rayleigh-Benard convection. So now I told you, if you are seeing from the top, you'll see hexagons. What do you mean by that? When the fluid is heated at the bottom, the fluid parcel moves up and falls towards the sides. So the sides of the hexagon, what you see, are the places from the center where the fluid falls outside. So if you see from the top, you'll see an hexagonal pattern. Whereas if you see the case of rolls, I talked to you about rolls, you'll see that the fluid parcel simply move up and come down, move up and come down. Okay, so you'll see nice rolls over here, and these can be captured only when the photograph is taken from the sides. Hexagons can be captured only when they are taken from the top. Likewise, there are other patterns which are there. Okay, many variants of hexagons and squares and rectangles as well. And you should note here that a slight disturbance of this Rayleigh-Benard system, which was showing rolls, can give rise to hexagons. So this the experimental configuration is quite sensitive. Okay, so what can those be? Now, for example, if I replace this top plexiglass and expose the system to the atmosphere, so then we'll see that surface tension becomes important, and when surface tension is there, it is hexagons that we see. Okay, or we can have, for example, plates, bounding plates to be thick. Okay, so any such thing which is not, not the one used in order to get rolls, then you'll definitely get other patterns like the hexagons. Hexagons are preferred in many cases, but they are the most difficult ones to investigate theoretically. Not very difficult, but they're quite difficult compared to the rolls. So you see, aesthetically, this problem is very nice. So you'll see a number of patterns, rolls, hexagons, squares, rectangles. Now, in order to vibrate the system, there are a number of vibrating tables which people design and pass it on to you. Here you see, this is not the exact table that is used for Rayleigh-Benard convection. Much more sophisticated one is required, but just to give an idea, so this is what you have. So you'll see that there are some dampers which are there here to see that the vibrations do not give rise to noise. The table on which the Rayleigh-Benard configuration is placed, the table is made to vibrate in a very nice manner. For example, if you see a sinusoidal wave, what happens? If you see a sinusoidal wave, you will see that the amplitude increases, goes up to a certain maximum point, then decreases. So these vibrations are done in exactly the same way. So periodically, so the amplitudes, if you check of these vibrations, they will be exactly that of a sinusoidal or a cosinusoidal. And what we proposed was, other than that is trigonometric, so you can have square, that is triangular, or even sawtooth. And if you want these tables to vibrate in a way which you want, you'll have to bring in a lot of additional electronics, and who better do this than our engineers. So now what happens here? When you vibrate the table in a very nice manner, why am I saying this? There must not be noise. The vibrations must be very, very gentle. The amplitude must be small. So when you say sinusoidal waves, the amplitude must be small. It's some sort of long waves. So they must be gently vibrated. The amplitude must be small, and the frequencies cannot be very, very large, mind you. Okay, because I told you the Rayleigh-Benard configuration is very sensitive. It has to be done in the most gentle of ways. So now this is one vibrating setup which you have, one vibrating table. What can be done is, you can have, for example, another vibrating table over this. So when you have one vibrating table and another vibrating platform on that, so together they give you a set of two vibrating things. The first and the second need not match in terms of frequency, in terms of amplitude, okay, in terms of the period, they need not match, or they may match perfectly well. If you have a sine in the first, you can have sine in the second. If you have sine in the first, you may have a non-sinusoidal in the second, and so on. So this is something which we thought would be interesting. So we added to the investigation. What previous investigations did, what they simply considered two trigonometric vibrations. So we consider non-sinusoidal vibrations, so two platforms vibrating independent of each other, okay, but can be regulated from the outside. So this is what is called this vibrating table. What happens now is when you see the system, it is not the usual gravity that you see, but you'll see additional gravity effects due to vibration. So those additional gravity effects are time dependent. So now if you manage your vibration in a nice manner, you can have time periodic oscillations, whether they are trigonometric or non-trigonometric, you can maintain that. So we are presenting here this particular work wherein some new idea is being tried in a theoretical way, and hopefully when the paper gets accepted, people would try this experimentally as well. And we also have plans to apply for a patent once the paper is accepted. So these are the things I already mentioned to you. We take either sine or cosine for the trigonometric. When it comes to non-sinusoidal, we take triangular, square, sawtooth type of that is oscillations. And you know now why we call it as modulation. Okay, so this is the sine wave. I'm sorry, when the figure was fitted to the slide, the square became a rectangle. I'm sorry about this, but anyway, I'm sure you'll understand that. So this is the triangular wave. So the sawtooth wave for you. So all these, it is obvious that we are taking the Fourier representation for them in our analysis. So I told you that we were the first to report such a work, but we did not consider two frequency, that is gravity modulation. It was single frequency one. Interesting results in that too. But here we have tried the two frequency modulation. So we wanted to see whether, single frequency modulation is known to stabilize the system. So when you say stabilize the system, what we are trying to delay the onset of convection, onset of instability. So thereby the that is Nusselt number is also reduced, the heat transfer. So when you have a two frequency modulation, does it enforce itself on the single frequency, on the first frequency, or is it that they act against each other? Okay, so they don't work in tandem. So that was our curiosity. So we did this. So this is the one I referred to earlier. This is single frequency modulation. So in this problem, you can have either harmonic instability or subharmonic. It depends. Subharmonic is a separate problem by itself. I'm not going to discuss about that. So this is the two frequency modulation that you have. So you'll get numbers like R1 and R2. And this I mentioned to you already. They use Floquet theory, and their analysis is a linear analysis. Okay. And as I told you, Renu Bajaj is the pioneer in this, and that is the only work available. Okay. So this is what you have. So the need for the study is because this is an emerging area, okay, and there is not much of literature available, and experimentally also it is unexplored. So here we have two plates heated. T0 obviously is greater than T1 for the instability to be there. Gravity is vertically downwards. Distance between the plates is D. So we are considering a two-dimensional study, the simplest one, in order to get an idea as to how gravity modulation works in this problem. Subsequently, we intend to go three-dimensional and study hexagons as well in this important problem. Let us see how it goes. So the usual conservation of mass, conservation of linear momentum, conservation of energy, equation of state. Here, this is a pure liquid. I mean, we don't have any nanoparticles. We don't have any porous media, no magnetic field, no rotation. This is an original problem which we have initiated. So, in addition to gravity, we are bringing in that is a gravity modulation. So, in the basic state, what happens till the onset of instability? It is one of conduction. So you see that the temperature is linear because second derivative is 0. So we have written it over here. So the density, the fluid is density stratified due to temperature. So that density stratification gives rise to buoyancy. So the effective gravity is this. I wrote this down already. Okay. So we have two frequencies. Now we'll make combinations of sine and non-sinusoidal. So one is G1, that is sine, and the other is G2, which is non-sinusoidal or sinusoidal. So we make combinations like this: sine and sine, or sine and square, or triangular, or sawtooth. Okay, so combinations like this. Lower one sine, the upper one is either sine, square, triangular, or sawtooth, like that. So we make stability analysis. So the usual thing. So non-dimensionalized, introduce stream function because it is a two-dimensional study. Then after introducing the stream function, what you essentially get is a vorticity stream function formulation like this. I don't have the time to explain in great detail. So you have second order, fourth order in Z, second order in temperature for Z. So you have periodicity conditions in X. So that makes all the boundary conditions and periodic conditions to obtain a particular solution. Because we have not specified any initial conditions, we do get a dynamical system. So this is the classical linear stability analysis. I'll simply rush through. We get the correction Rayleigh number, which comes because of the gravity modulation, two frequency gravity modulation, and we are able to say for exactly where for what value of the Rayleigh number instability sets in. So all these combinations have been worked out in great detail. Okay, and so this is the expression for the correction Rayleigh number which we obtained. So for all the combinations, we can we know what these BIs are. Okay, depending on what combination it is, we'll get the appropriate value of BI. This is merely routine calculation. Okay, so this is what you have. So now you see that if B1 equal to B2, then you would get the correction Rayleigh number with sine and sine. If chi equal to 0, then we get single frequency results, classical one. Okay, and if delta 1 equal to 0, RA2C equal to 0, obviously there is nothing to correct. So you get the results of no modulation case. Now we do a linear stability analysis in the usual way by taking a double Fourier series. This spectral method will give you the Lorentz system with this two frequency modulation term here, where I'm sorry, FIT I should have recorded. It is there in the previous slide. So now, having known the amplitudes, I can find out the temperature. So I can find out thereby the Nusselt number. So I'll also use mean Nusselt number here, which is a time average Nusselt number. That will give me a better idea about the effects, various effects of amplitude, frequency, and the phase, which influence the Nusselt number. Okay, Prandtl number also. Okay, so this is what you have. So now what you see is the discussion of the results will be on studying the influence of two frequency modulation as a combination of two sinusoidal waveforms, or it could be the discussion of results based on a combination of sinusoidal and non-sinusoidal waveforms, or it could be both of them being non-sinusoidal waveforms as well. I'm sorry, I should have written a 3 here. It's fine. I mean, it's understandable. You'll see in the results. So let us see this result now. Two frequency modulation as a combination of sinusoidal waveform. Both are sinusoidal, that is. So you'll see that the results of the two differ when you have this. I'm sorry, there is some noise. So you'll see this is very important result. When you have no modulation, the critical what you get will be less than what you obtain using single frequency modulation, and that will be much less than what you see in the case of the two frequency modulation. Okay, this other result is too technical. I'll just drop that. So these are all routine figures that you get. So you see here that as a result of the modulation, the mean Nusselt number decreases over here. Okay, it is to be expected because due to the presence of two frequency modulation, the critical Rayleigh number increases. So this is what you have. It is delayed. So those contributions are there. Now, I'll not go into these details. These we simply picked from our paper. I'll present you some very important results. So, if you observe the results of the paper, this dual nature of Prandtl number is a very important result because it's a surprising one. If you see single frequency, you don't see this. Okay, so you see that when the frequency is, this is non-dimensional frequency, when you see the frequency is less than 1.5, so you see that as PR increases, Ra2C decreases. Okay, it's meaning depending on the fluid, we can have either advanced convection or delayed convection by adjusting the frequency of the oscillations. So when omega is greater than 1.5, the effect of PR on Ra2C. So if the higher frequency oscillations are not of any interest. Why does this thing happen? This happens because the pattern itself vanishes, okay, giving rise to yet another pattern. So the theory that we have formulated to take care of the experiment which we thought we are representing, that itself ceases to exist. So the effect of PR on Ra2C dies off. So for large frequencies, you don't see the effect of modulation. So this dual nature of frequency is a very important result that we need to see. So now in the analysis, we come across two numbers, R1 and R2, and we basically took this to consider harmonics, and as a result of which R1 and R2 have to be integers if you have to consider harmonics, and R1 and R2 have to be co-prime. The analysis requires that. We can either take R1 less than R2 or R1 greater than R2. We have assumed R1 less than R2 here. And if you increase R1 or R2, meaning it is increase in the frequency, so the destabilization is there. They significantly increase the amount of heat transport. Okay, so this is an external mechanism of oscillations using which you can either increase or decrease the extent of instability, increase or decrease the amount of heat transport in the system. Okay, so this is what you have. This is exactly what I am mentioning here. So change in R1 and R2. We will not worry about this right now. What is important is this. So they significantly contribute. The two combinations of the oscillations, they significantly contribute towards either reducing the extent of heat transport or enhancing the extent of heat transport. So these are the things that we have. Okay, so I now I'll end up um, by saying that the combination of square-square waveforms yields the highest value of RC, thus making it the most stabilizing combination. And combination of sinusoidal with non-sinusoidal gives higher stability bounds compared to sine-sine combinations. Okay, so this is what you have. So some nice results. Okay, if you take two sinusoidal, well, destabilizes the system. Sine triangular and sines with the sawtooth, they give exactly the same results most of the times. And heat transfer is maximum for the combination of triangular waveform with sinusoidal and other non-sinusoidal forms. Okay, so these tables tell you the same thing. And the order of the modulation is also important. See, suppose you consider, say, two vibrations. One is sinusoidal, the other is non-sinusoidal. What Nusselt number we obtain for this is not the same as, suppose I consider non-sinusoidal below and sinusoidal above. It's not the same. Surprisingly, there are many other surprising results. Hopefully, in the paper you can see in the physics of fluids shortly. I am hopeful that it goes through. What is very important is the amplitudes and the frequency, the phase, everything will have to be handled in such a way that there is some harmonious combination of these two waveforms, and so that we get either maximum heat transport or minimum heat transport depending on an application. When you want heat storage, you would require to have minimum heat transport. When you want maximum heat transported, meaning you want to regulate the temperature in the system, you want heat to go out of the system, so you require maximum heat transport. So the vibrations of the system can be effectively used in achieving this depending on the application. Okay, these are all the things which I've already told you. So I'll stop here, and I hope I provided to you some useful new information, both from the mathematics and from the engineering point of view. And if there are any questions, I would be very, very happy to answer. If I cannot answer, I'll get back to you. You can just take my email from any one of my papers and email me. I'll get back to you on the question that you asked in case I don't have a reply. Thank you very much.
Thank you, sir. That was a wonderful lecture. I hope all our faculty and researchers have gained a very good knowledge out of it, and I am certain that they will come up with new ideas using your lecture. I hope all the faculty, if you have got any questions, I'll give you 2 minutes. You can ask the questions. Anybody, or otherwise you can send it through, like you can chat it. I'll pass it on to professor, and certainly I can do that. Any question?
Can you hear me? Good morning.
Yeah.
Sir, I am Dr. S.A. Mohan Krishna from Vidyavardhaka College of Engineering, Mysore.
Yeah. Yeah, I'm hearing you.
Yeah. We can. Tell me. You can.
The session which was Rayleigh-Benard convection, so which is a type of natural convection which has a very bright research prospect. So we are all very fortunate to listen to your talk, sir. It was absolutely tremendous. Sir, for the present researchers, do you really recommend to carry out research in Rayleigh-Benard convection? Is there a bright prospect in this, sir?
See, any field, for example, would have a lot of unsolved problems, and Rayleigh-Benard convection is no different.
Okay.
There are a number of problems which are as yet unexplored. Two-dimensional Rayleigh-Benard itself, there are a number of problems, and when you go three-dimensional, the possibilities are immense. Now, I would say that if you want to publish in top-class journals these days, we will eventually have to go to a three-dimensional unsteady problem, and that would require, say, the pattern in the form of not rolls but hexagons. Okay, so that's a nice problem to take up. For youngsters, I would suggest that you start with something on those lines. You can definitely do a good job out of it.
Also, you have quoted wonderful references, the research papers that have been published in a top class journal. Thank you very much for your knowledge sharing, sir. So we are really blessed today to have in this session, sir. Thank you very much.
Thank you, Dr. Mohan Krishna.
I think there is no more questions.
Sir, can you please contact number, sir, if possible?
Yeah, with this, I'll conclude the session. I'm really grateful to Professor Dr. Pradeep Siddeshwar. He is the main inspiration for me. See, I started with just two faculty, two resource persons. With his able advice, I could able to have nearly 25, more than 25 resource persons, that too 5 from different country, people from different countries are also. He only suggested, and one more greatness of his is, see, once I quoted his name that he has referred, he has given me your suggested your name. Readily they accepted. That shows his greatness actually. With this, I am really grateful to you, sir. Thank you, sir. I'll stop now. I conclude this session, sir. Thank you, sir.
Thank you. Thank you very much. Thank you.
Thank you. So I'll ask the participants to log in using the third login ID. Please do that. Dr. Sadashiva, Principal of Vidyavardhaka College of Engineering, is delivering a lecture on discretization, which is very much important for computational fluid dynamics persons. It is grid generation. Certainly, it is very much useful for CFD. Thank you. Thank you, sir.